Everyone, I'm Mrs. Jeevan and I'm talking about the universe today. This is Texas Standard 8.8a, the universe in the HR diagram. Describe components of the universe, including stars, nebula, and galaxies, and use models such as the Hertzsprung-Russell diagram for classification. Here's a list of things we should know or do, but to simplify, I know how to describe components of the universe, including stars, nebula, and galaxies, and use models such as the Hertzsprung-Russell diagram for classification when I can successfully place the objects of the universe in order based on their relative size, interpret an HR diagram to classify a star when given the star's temperature and luminosity, and compare and contrast two stars. I'll also throw in there if I know the definitions of all these vocabulary words. So we're going to start with the objects of the universe. The universe is everything. It's all matter and space. So that includes our galaxies, solar systems, planets, stars, and even ourselves. The Big Bang Theory is the theory that the universe started off compact and it's expanding, and that's kind of in this bottom right picture. So it started off very quickly, and then billions of years later we have like star formations and us. And we're able to know this because by using our electromagnetic spectrum, we can see that galaxies are redshifted, which means they're actually moving away from us. Most of the universe is empty, meaning it's just full of space and it's a vacuum. So like most of everything in the universe is just empty. And what's holding everything together is gravity. And the top right picture kind of shows this idea that there's this force of gravity that our planet has. But we also know that the sun has gravity. So every object in our universe has a gravitational pull, and that's kind of what's holding things together and giving structure. Just as a reminder, we don't know that much about the universe. This picture kind of helps represent that. Here is what we estimate is the size of the universe, and here's what we've observed. We have equipment that can see so far. We don't have that technology right now. So we're going to start off by those objects. Why did it go with moon first? I don't know. It's really doing a weird thing. That's exciting. Oh well. Anywho, so we're going to start from the smallest. So this is really small, which is why I'm trying to write an S. Ooh, that was a bad S. Small. Okay, so small meteor. And that's what falls through our atmosphere and catches on fire. So shooting stars. A comet contains ice. And because of that ice, when we look at a comet, it has a tail. And that tail is from the vapor from the ice. An asteroid is bigger than that, and an asteroid is really just a rock. And it does orbit in a predictable way, just like a comet does. We know what a moon is. That's why I didn't write it out, but we have a moon around Earth, and then Jupiter has more moons than we do. Not every planet has to have a moon. Bigger than a moon, typically, is our planets, and these planets are going to be orbiting some kind of a star or binary star. Binary star means we have two stars instead of just one. Our solar system just has one star, and that's our sun. Bigger than a planet, typically, is a star, and a star is just a sphere of hot gas releasing energy through nuclear reactions, and those nuclear reactions are fission. So here I'm drawing my little star. It's a sphere, and there's energy in it because of something called fusion. Fusion is when we have hydrogen, and it combines with another hydrogen, and it creates a bigger atom, and that bigger atom it creates is helium. So most of stars are composed of hydrogen and helium. Eventually, they'll keep combining to make bigger elements like iron. Bigger than a star is a solar system. So we have our star in the middle, and then we have our celestial bodies orbiting that star. And then bigger than a solar system is a galaxy. So galaxies are composed of gas, dust, stars, dark matter, etc. And we're going to get more in depth with galaxies in the future slides. So here's kind of like a picture showing how things get bigger. So asteroid is smaller than moon. Moon is bigger than asteroid. Then the planet's bigger than the moon. A star is bigger than a planet. A solar system is bigger than a star. And a galaxy is bigger than a solar system. And finally, the biggest of all of these is the universe, which contains everything. And this is again kind of showing this. So here's our Earth, which is inside of our solar system. And then there's all these other interstellar neighborhoods. So there's all these other stars around us. And then this is where we are on the Milky Way galaxy. And so the Milky Way galaxy, it's what we would call a spiral galaxy. So we see these arms are coming off like that. And we are located on one of the arms. But then you have all of these galaxies close together. And then it just gets closer and closer. And then we finally we've zoomed out far enough so that we were able to see the entire universe. Well, the observable part of the universe. So again, this is helping us understand all the different parts of our universe. So there are three major types of galaxies. I don't know why it's going in weird order. And we determine them by the size and shape, which helps for us to figure out their age. The center of the galaxy is really dense and has a very strong gravitational pull. So the center of the galaxy is actually actively pulling in on things. So here's my center. It's trying to pull in and get really compact. It's kind of like a magnet. It's really attracting everything. That typically means that there's a black hole in the center of the galaxy. There are three shapes, like I was saying: irregular, spiral, and elliptical. But before we get into that, there is this one vocabulary word that we all have to learn, and it's nebula. A nebula is just where a star is born. It's the birthplace of a star. You might hear it referred to as something, a stellar nursery. Let's see if I can spell that out. Stellar nurse. Okay, that's funny. That's close enough to nursery. It's irregular in size and shape, so it doesn't have any structure yet. It's actually not emitting its own light. It's really reflecting the light of other stars close by. Most of those beautiful pictures that we see that we think are of the universe or the galaxy, these are actually all pictures of nebulas. Inside of a nebula is a bunch of dust, and this dust is typically carbon, gas, and plasma. So we have dust, which is carbon. It's also hydrogen and helium, gas, and plasma. And all this is swirling around, and eventually it gets hot enough and dense enough that we can form a star. Now let's focus in on the galaxies. The first type of galaxy is the irregular. It's the youngest galaxy, and it has an irregular shape, and that's why it's called an irregular galaxy. It contains a lot of nebulas, and it contains a lot of dust. There's just not a lot of structure there. There aren't a lot of things in the galaxy. So it looks just, if I were to draw it, I would just draw kind of like a line, like a squiggle. There's no real shape to it. Now, as it gains shape and it gets older, the irregular galaxy has some gravity in the center, and it's going to start pulling in from on the outside in. But until then, it's going to be the largest of our galaxies. It's really big because it doesn't have a lot of structure. As it starts to pull in and fall in on itself, we get a spiral galaxy. So basically, my spiral galaxy has pulled in, and as it's pulling in, it gets more and more structure, and it looks kind of like a spiral. So it has a middle, which is dense, and then it has the circular center with arms spiraling out. So if I were to draw it, I would show here are the arms, and it looks something like that. So the Milky Way is the galaxy where we find the planet Earth, and Earth is located on an arm of the Milky Way galaxy. So it's not in the center, it's on an arm, which means it's part of the younger part of the galaxy. And our galaxy is going to get more compact and it's going to get even smaller. When it does that, we form an elliptical galaxy. An ellipse is just like a circle or an oval. And these are the oldest galaxies. They're circular or oval in shape. You might think they look somewhat like a football. And if it's really circular, that means it's really old. So this is a little bit more oval-like. So it's not as old as this one, which is more of a circle. And these are the smallest of the galaxies. So they're really small, they're very circular, and they're very old. And that wraps it up with the objects of the universe. And we've been talking about HR diagram in class. We use this to sort stars. And it's also used to predict a star's size, color, spectral class, age, stage in the life cycle. So stars have life cycles kind of like humans do, where they're young and they get older and they basically die. HR diagram is actually standing for Hertzsprung-Russell diagram, but because it's a lot of writing, we just call it HR diagram. When you look at the structure of an HR diagram, the x-axis will be temperature and or color and or spectral class. But the weird part is that temperature is backwards. What that means is over on the left side, it's 30,000 Kelvin, but on the right side, it's 2,500 Kelvin. So it's actually decreasing as you go from left to right. The y-axis is luminosity and or absolute magnitude and or apparent magnitude. So luminosity is on the right side. Luminosity is just describing the brightness. Same with absolute and apparent magnitude. They all three describe brightness, but they're measured in different ways. So spectral class, luminosity, that's brightness. Spectral class is just kind of like labeling what the star is. Absolute magnitude, apparent magnitude, those are all new too. So these are really just brightness, but measured in a different way. Absolute and apparent. Absolute means it's like measured and calculated, whereas apparent is what it looks like to us. I'm going to draw an eye to kind of represent that. Here's my eye. So it's what it looks like to us from Earth. Versus absolute magnitude. Absolute magnitude means I've done some kind of math. There are a couple of trends on the HR diagram. We know that color can predict temperature. So on the right side where it's orange and red, that's going to be where we have colder stars. Whereas on the left side where we have the blue stars, that's going to be hot. Also, size can predict luminosity. Bigger stars are going to be brighter. So they are at the top. We see these giants. They just look big. So the bigger the star, the brighter it is. So that means stars at the bottom that are small, these are considered to be dim. So they're not that bright. If we look at an HR diagram, there are 4 major groups I want us to focus in on. Those 4 groups are the main sequence, supergiants, giants, and white dwarfs. When we have a nebula, a star is born, and that star is going to start down here. And it's going to, as it ages, it goes up the main sequence. And depending on its size, it'll become either a supergiant or a giant star. So huge stars become supergiants, and then they follow a different pattern. But an average sized star, like our sun, will become a giant. And then it'll spend a certain amount of time as a giant. Eventually, after that, it becomes a white dwarf. So basically, it starts to run out of fuel, it collapses in on itself, so it gets a lot smaller, it's very dense, it's very hot. So again, we start up down here, we go up the main sequence, If we're really big, we become a supergiant. If we're average, we become a red giant. And then after a red giant, we become a white dwarf. We meaning the star. So 90% of all stars in the universe are part of the main sequence. That's where a star spends the majority of its life cycle. This includes our sun. Here's our sun. And there's a large variety of temperature and brightness. In this section of the HR diagram, there is a relationship between temperature and brightness, but only here in main sequence. That relationship, though, if you look at our stars in this picture, it's still mostly based off of size. The bigger the star, the brighter the star. Right, next we have the red giant star. That's right here. So the sun, for example, will eventually become a red giant. And it's large, it's bright, it's normally a cooler temperature. Here's how big the sun is compared to how big a red giant is. So red giant is significantly larger. Again, we're following our sun. It becomes a giant, and now it's getting really old, so it becomes a white dwarf. This is the end of an average star's life cycle. It's small and dim, but very hot. It's so small, it's collapsed in on itself that it's similar in size to the Earth. So it's really similar to an Earth, but it's a star. So it's a lot of heat in a very small space. If we are not a star and we're a very large, not the sun and we're a very large star, we might become a supergiant. And a supergiant will be very large, very bright, and normally a cooler temperature. So here is a better explanation of the star's life cycle. You do not have to have this memorized. This is just for those people who really want to know. It explains where a white dwarf eventually becomes a black dwarf. It shows you where we can get a black hole. So for example, I start at nebula, and then I eventually become something called a protostar. After that, I can become a main sequence, like the sun, and it goes red giant, to white dwarf, to black dwarf. And then there's some different pathways here. It doesn't really follow this path every single time. It really just depends on what you're starting with, and that's kind of shown in this picture. So here's the sun, protostar to main sequence, to red giant, to planetary nebula, to white dwarf. That's what the sun will probably follow. Just to recap, the universe is everything, including the empty space, and it's made out of galaxies, and those galaxies contain solar systems. And the solar systems contain stars which are orbited around by planets, and these planets can have moons that orbit around them. We use the HR diagram to organize stars by luminosity and temperature, and it can be used to categorize stars as a white dwarf, main sequence, giant, or supergiant. Finally, HR diagrams can be used to predict the color and relative size of a star. Keep in mind, you still need to know what a nebula is. It's the birthplace of a star. And you should be able to organize the components of the universe in order of size.